in on the equations of change for multi-component systems. So this is our last set of equations that we're going to learn for the class, as far as I know. So we're going to start out and we're going to learn about mass transport equations. And I anticipate we'll get through probably most of this today, but I guess we'll get to it here. Maybe not like there, maybe we'll get to C. And then we're going to talk on Monday about examples, and we'll talk some about what happens now in multi-component systems. We have mixtures when we put in fluid flow and heat transfer, and what are the other terms that come in there. And then we'll finally have sort of all the equations. And then hopefully we get through that on Monday, and Wednesday we'll have a review, and Friday we'll have an exam. And so what I want to do is I want to take your homework that says it's due Monday, and I want to make it due Wednesday. Okay, that has to do with some of this stuff. Let's just make sure we get all the way through that, and then we'll make it due Wednesday, and we'll have a review on Wednesday. Does that sound good? Okay. No one's really mad if I'm making homework due later, especially if it's not due today. Right? If it was due today, you'd be like, I worked hard, but no, we'll make it due Wednesday. Okay. All right. Who do we got online today? Zach and Dan. Perfect. No Mehmet today? Okay.
I was on yesterday.
So, yeah, so in the department, we have, like, when you're pre-tenure, actually, and post-tenure, we have peer reviewers that come to the class and observe what you're doing. And so then when I go up for tenure, they write a letter and say whether I'm a good teacher or not. So Matt's been coming to my classes for a couple of years now. So I have Matt, and then I also have Tommy as my peer mentor. So he's like the person I'm supposed to go to with questions. Well, I go whine to him. My graduate students annoy me. Grants reject me. I looked at you, ChEn. That's right. But I do. You know, I see. Like I just fouled Tommy harder at basketball. That's my outlet. I blocked it pretty good today. It's pretty fun. All right, mass transport equations. He made a 3 in my face, so he made it 4. So I'm gonna make 3 threes today, Doug. All right, go ahead, Tommy. Let's see. I had to guard it for a while. Okay. So mass transport equations. So let's start out with A, species, mass, and movements. Oh, I got no good markers today. All right, so we've done, this is our last balance, I hope, for the year, okay? We'll go through it one more time, really quickly. So we've got, he's gonna go get me. Thanks, Junior. Let's switch rooms. When she comes back, she'll be still. Yeah. Okay, so we've got ourselves a little cube. X, Y, Z. One time I did that to my wife. She went in to go get some from church, like we were on our way to church. I took the car with all the kids and I just drove around the corner. She came out, was looking around, couldn't find us. You know, we were like a few minutes early. So the kids were like, Dad, don't do it. Mom can't find us. And they were all freaking out. Well, I got in trouble for that. But anyway, that was kind of fun. So we've got a flux, for example, of species alpha in the x direction. I guess we call this x, y, z, right? This one, x plus delta x, y plus delta y, z plus delta z. Up in that back corner, right? Now every time I get in the car to go to church, sometimes my kids go, trick mom, trick mom. Not too much trouble. Okay, and then we have coming out an alpha x, x plus delta x, and we multiply by the area to get the flow, right? Delta y, delta z. Thanks, Junior. 3 of them. Holy cow. Y, delta z. This one, it feels like it's new, but if you store them like this, all the stuff runs that way. So we'll keep it like that. The next person who uses it will have better luck. All right. Okay, and so remember that N, oh, that one's better, is the total flux of alpha. And we might have also chemical reactions happening inside the box. So we'll call that R alpha. We'll just call that chemical reactions. All right. So we have our differential volume, and we're going to write in minus out plus generation equals accumulation. So we got to write our in terms, our out terms, generation terms. Right? So that's lots of terms. So I'll just write it down real quick. We've got n alpha x at x delta y delta z. That's an in. And on the other side, we have an out n alpha x at x plus delta x delta y delta z plus, then we have the one at y and alpha y at y delta x delta z minus n alpha y at y plus delta y delta x delta z. And then we have the term for z, right? And alpha z at z delta x delta y minus n alpha z at z plus delta z delta x delta y. Okay, so those are all of our flux terms plus reaction term, right? R alpha. That'll be like a reaction rate per volume. So we'll be multiplied by delta x, delta y, delta z. And all of that should equal the time rate of change of rho alpha, delta x, delta y, delta z. Because that's the mass of alpha, right? Okay, so we have those terms, and we do what we've done. We divide by delta x, delta y, delta z. We take the limit at delta x, delta y, delta z go to 0. And that gives us minus the partial derivative. Partial derivative of n alpha x minus partial derivative n alpha y minus partial derivative n alpha z, with respect to x, y, z respectively, plus the reaction, right, equal to the derivative of the density with respect to time. Okay? And we can rewrite that using our divergence operator, right? Like we've seen. I'm going to put the time derivative on the left-hand side like we normally do. Rho alpha to t minus del dot n of alpha plus r alpha. Sure I didn't screw it up. Okay, and that's good for alpha is equal to 1 to however many species there are, ns species. All right. Pretty easy, right? Yeah, please.
So with our system, if we defined it the other way, so that the fluxes were kind of going, like, for example, in the x direction instead of left to right, right to left, would that eliminate the negative in that equation? And how would that cause different implications? I guess I was just thinking if we tried to define the system differently, if it would change the equation in the end.
Yeah, so you have to be, so when you think about the flux and then you want to get to like a mass, like a flow rate or something, you're going to have this flux alpha, and then you need to do a dot product with the unit normal surface, okay? And that's often an N2, so that's kind of a terrible notation, right? But it turns out that the way that that's defined, here you've got a unit normal this way. So it's minus n dot, and I'll put a u there for the unit normal, okay? And so even though I'm writing this here and kind of making it intuitive that it's like that, this flow defined this way sets the minus sign like that. Okay. And so that's what the flow has to be sort of through that surface. And so even if the flux is in the other direction, that the minus sign should still stay. Does that make sense? Yeah. Good question. Yeah, this problem, we start to do it a lot of times, and then you start to think a little more about the assumptions of the derivation, and you're like, well, that's a little simple. I can imagine drawing my arrows the other way, right? So what's wrong with that? Okay, so now the only last thing we have to do here to get sort of or equivalent of the Cauchy momentum equation or of the total energy equation is to plug in the total flux. Yes.
Your NS over there is that number of species?
Yeah, number of species. Okay. So remember that the total flux of alpha, I left alpha there, N alpha is rho alpha V plus J alpha, where J is diffusive flux. So I plug that in here, and I get d rho alpha T is equal to minus del dot, and I have rho alpha V minus del dot J alpha plus RA. Okay, so this we'll call our species mass balance. Okay, or in the equation of continuity for species alpha. So I don't want to write that out. Equation of continuity for alpha. Okay, and like I said, this is analogous to our Cauchy momentum equation. So you remember, the Cauchy momentum equation was the equation in fluids before we plugged in Newton's law of viscosity, right? We also had, you can think about this as like the internal energy equation we eventually got to in the energy balance, right? Where before we plugged in Fourier's law, we had that internal energy equation that we had to mess with. This is the one for mass transfer, okay? So we haven't plugged in the flux yet, but as long, we've got everything else. This is our balance, okay? So let me make just a few comments about this. Okay, so the first is we can do an identical procedure for moles. Right, so you remember that's one of the things that's with mass transfers, we got to pick on my densities or my concentrations, right? And which am I going to do it in? So we could go through and we could do this whole thing again for moles. Let's not, right? But we can write down an equation that we get from that. So we get dC alpha T is equal to minus del dot C alpha V star minus del dot J alpha star, where now I have a big J, which is what they use for first year Lightfoot, plus a big R alpha. Okay, so we can do the same thing for moles. Okay, here. Okay, second comment is we can sum the species balance. Okay, so we can write the sum over all the alphas. Alpha is equal to 1 to ns, right, of that entire equation. Right, I'm just going to put, that in parentheses because I don't want to write it out. All right, so let's think about that for a second. So what happens? We have a sum, and it comes on the left-hand side over here. Well, we can move the sum inside the derivative just fine, right? That's a time derivative. So then we have the sum of all the real alphas. Well, what's the sum of all the real alphas? D rho dt. So I get d rho dt. Okay. The next one is I have a sum over all the species of a divergence of rho alpha b. Well, similar thing there, right? I move the sum inside the derivative, and I can sum over the alphas, and I get rho v. So I get minus del dot rho v. Okay. The next one is this guy. I have a sum over all this the diffusive fluxes. So remember, we defined the diffusive fluxes such that they were all relative to the mass average velocity. And so that means that they all had to sum to 0, right? So when we sum them up, that term's 0. That one's not there. And then when I sum over all the reactions on a mass basis, if I sum over all the reactions, that has to go away, right? Because I can't have a chemical reaction that's producing mass. So that's it. That's what I get right there. If I sum over everybody. Okay, and that should look familiar to us, right? That is the total continuity equation, right? We saw this in momentum lectures, right? So hopefully that makes us feel good, right? We did the same balance before, but on the total mass. Now we do it on the species. Get a couple extra terms in there, but when we sum it up, we get that. Okay? And then the final comment is we can do the same thing for moles. Okay? But in that case, we end up with dc dt is equal to minus del dot c v star. Okay, where v star is the mole averaged velocity, right? The concentration average velocity, what is it? The mole fraction in front. And then we also get a reaction term, which is the sum of all the reactions, right? Because you can create moles in a differential area. That's not a big deal. Okay? Not sweat so much anymore. Okay. All right. So that's the continuity equation written in all bases. Any questions about that? Pretty straightforward to hear. Okay. All right. So let's go on and do B. Action equation. All right. So if we have our Cauchy momentum analogy, we need to get to our Navier-Stokes, right? We need to get to the thing where we have equations in terms of stuff we can solve. So we need Fick's law. Okay. But so we've been writing Fick's law as J alpha is equal to minus rho DAB gradient of mass fraction W alpha. And that's what we've been writing as Fick's law. The problem with this is that this is only good for a binary system. Okay, so this is binary only. Okay, if you want to do a multi-component system, you got to make it messier. So you're going to write instead J alpha is equal to minus a sum over beta from 1 to ns minus 1 rho d alpha beta gradient of W beta. Okay, so if I think about this, right, that means that there is one of these terms, okay, for all of the other species but one. So look, okay, so this one, if you think here, when I had binary, I just had one, okay? And now in this case, I've got, if I have a ternary system, I have two. So I essentially have this 2 by 2 matrix that I have to solve, okay? And so in this one, you have to, like, the notation here is a little bit funky. So I couldn't think of a better way to write this. So here, we're like, Bergster and Leif would call that DAB. You can think of it as like DA in a B solvent, right? This alpha beta here, though, this is like D alpha beta in, you know, whatever solvent, right? So if I had a ternary system ABC, I would do this, you know, and have DAB and D, you know, and then, or DAA and DAB, right? And then DBA and DBB, right? And so I have like those four that are going on, but all of those are in C, right? So in that notation, this one should be like DAA in B, if that makes sense. So I don't know if I lost you. I see you nodding. I confuse you about that. Do I need to write it out? Like, right, minus, if I had J1, I would have minus rho D1, you know, beta, I guess I'd stop there. So now I have D1 1 minus rho D1 2 grad W1 2. Okay. And I still have a W3. That would be it, you know, for a ternary system. That would be NS equals 2. Is that clear as mud? I'm kind of seeing like staring. Not sure I'm happy about it. Okay. What's going on here is that this is telling you that there is a diffusion of species A, even if there's gradients of species B, right, that are independent of the gradients of species A. So in a binary system, if I have a gradient of A, I also have a gradient of B. They have to be inverse, right? But in a ternary or quaternary system, I can have all these other gradients. And so this one gradient over here of this can actually cause a diffusion of the other thing. It's a little weird, okay? Usually the D11s, the diagonal diffusion coefficients, are an order of magnitude larger than the off-diagonal ones, okay? So writing down something like this in a multi-component system is a simplification, right? Because now you're assuming that the diffusion coefficients on that diagonal are dominant over the other ones, okay? All right, so if we do that, we can plug that into our equation up in the corner. But it's also useful to rearrange this guy up here, these two terms, okay, to try and get something that looks like a material derivative. We can pull out some chunks out of it. So let me just show you what that looks like real quick. Okay, so if I write d rho alpha dt plus del dot rho alpha v, I can use the product rule of this, and I can write this as, remember that rho alpha is equal, rho alpha over rho is equal to W alpha, right? So I can take that and substitute it in. So now I get d rho W alpha dt plus L dot rho W alpha v. And then I can use the product rule on these. And I get W alpha d rho dt plus rho dw alpha dt plus, I don't know which one, I keep rho and v. I have rho dot grad w alpha plus w alpha del dot rho v. Okay, so I just expanded that out with the product rule. And now I can collect the terms that have the rho's in front and the terms that have the w alpha. So I collect the rho's over here. So I have rho d w alpha t plus v dot grad w alpha plus, and then over here I'll have w alpha multiplied d rho dt plus del dot rho v. Okay. And we just said that the continuity equation, we reminded ourselves that d rho dt is minus del dot rho v, so that's 0. Right, by total continuity, and I just have that piece left. Yes.
This equation is cool. It's not equal to 0.
So I'm just taking these two terms. I just moved this one over to the left-hand side. Okay. And so I'm going to take, since I just showed that that part's 0, now I can take those two terms and I can just substitute that in instead. Right? And this is rho big D W alpha. Right? That's what the definition of my material. So let me just write that below here. So I said, now I have d W alpha dt is equal to, and then I have minus, there's a minus sign in front there. So I have L dot, and then I'll put a bracket, sum over J, or no, I'm doing beta. Beta is equal from 1 to ns minus 1, right? Rho d alpha beta grad w beta close brace plus r alpha. Okay, let's screw that up. Okay, so there is our Navier-Stokes-like equation. It's all in terms of concentrations, right? Yes.
You forget the row in the front.
Yes. Thank you. I did. Okay. And so I'm going to call this, I don't know, the book has a terrible name for it. I don't even remember what it is. But I'm going to call this the convection fusion equation. I think obvious reason for the second. Okay. And I may call this the convection diffusion reaction equation. Okay. If we include the reaction term. Okay. Sometimes there's no chemical reactions, right? So it's just convection diffusion. So I'm going to abbreviate that for this lecture as convection. Okay. All right. So one quick comment about this. So we can also, just like we did this in mass units, we can write this in mole units, right? So that's the comment. It's mole units. And I'm going to write that one out. Rho dc alpha dt plus v star dot grad c alpha is equal to L dot sum beta is equal to 1 to ns minus 1 c d alpha beta grad x beta close brace plus r alpha minus X alpha beta is equal to 1 to ns of r beta. If you can't see that on the internet, let me know, and I can rewrite some of it. Okay, so there's a couple things to just kind of note about the mole version of this. Okay, first thing is that because you have this V star, this isn't the material derivative, right? Because the material derivative we define with a V here. Okay, so it's kind of like a mole averaged version of the material derivative, but it's not a material derivative. Okay, the next thing is over here, you get this extra term that comes out from the total continuity equation when you're doing this thing. Okay, that's a consequence of the fact that the sum of the reactions, is that from this part or is it from another part? Let me look. No, I think that's what it is. So when you find like the V star, there's this extra term that has to do reactions and it comes out. That's what that is in the ring. Okay, so it's just balancing all this stuff. Okay, so I didn't want to go through and do that whole derivation, but you can spend a little time if you want and prove to yourself that doing the same process we did for the mass. Okay, this same piece. Okay. All right. Questions about that? Good with these equations. We know where they come from. Assumptions are in them.
Dr. Tree,
Fire away.
how did you know that when you made the material derivative, how did you know that right term was 0?
How did I know that this one right here is 0? Yeah. Okay. This is the continuity equation, right?
Okay, so the
So
sum
I'm
of
going to
them.
move that over to the right side. That's 0. Okay. Well, I hadn't erased it yet. Good question. How was it on Wednesday with me on the internet? There were a few of you that were in here, right? You were in here, you were in here, you were in there. How was it? Is that weird?
A little bit.
Was it a little weird?
If we could understand you just fine, but it was just typing. I prefer this, but I think everything.
I prefer to be able to see people too. I had Zach, he was nodding along. That was good. Let's see. I remember. I think you were online. Were you online? Sometimes, anyway, it's easier to get a feel for how boring the lecture is when I'm in person. Like, all right, we're all dragging. That's Friday.
I felt like it was easier for me to get distracted.
Was it?
You were here yelling at us.
I wasn't like, Andrew, pay attention. Wake up. All right, simplifications. Okay, so just got 10 minutes left here. Let's see if we can get through this and maybe dimensional analysis will start. We'll finish that next time. Do some again. So for momentum, we did dimensional analysis first, and we saw that high and low Reynolds number mattered, right? Then for energy, we talked about gases, liquids, and solids. We saw some simplifications there. Okay, so similar kind of things apply here. High speed, low speed, gas, liquid, solid. Okay, but we also have to think about mixtures and what's going on in mixture properties, right? When we think about simplification. That said, our equation we had is simpler than like the energy equation we had, right? The energy equation had all these terms in it we had to figure out. So this one's a little bit easier, I think. So the first one, the first simplification is for solids and stationary. Okay, which also sometimes called quiescent. It's kind of a fun word. Liquids. Okay. And so I guess I just erased our equation. Maybe let me just write it off real quick here. Rho d w alpha. You don't need to write this down. It should just be in your notes. do sum over beta, rho d alpha beta, grad w beta plus r alpha. Okay, so that one I'm just kind of writing up for reference because I erased the other one, but okay, in stationary liquids or solids, right, the velocity is equal to 0. And so in that case, this guy turns into rho partial W alpha partial. Okay, we lose the convective part of that. That one's pretty easy simplification. Okay. The next one is even easier, which is no chemical reactions. Okay, that one's pretty easy. R alpha equals 0 if it doesn't participate in a chemical reaction. Okay, the third one is really important for this book, is a binary system. So I think there's only a few instances of problems that I saw, at least so far, that were not binary mixtures, that were like ternary mixtures. Okay, so in this case, we can simplify this guy a lot, and we get rho dw alpha d. We're back to the big D. Del dot rho, we're back to DAB, grad WA plus RA. Okay, so yes.
For liquids, the velocity is 0 too.
Say for stationary liquids.
Station.
Stationary liquids. Okay, so this could, for the binary system, I could have a binary liquid, right? The velocity is non-zero, stuff's moving, it's fine, right? That can happen. Okay, so binary system, this one's super equal. Okay, and then the other thing we got to think about here is dilute mixtures. Okay, so I'm going to have a dilute binary mixture. Okay, so if you remember when way back when we talked about diffusion coefficients, we talked about the difference between a self-diffusion coefficient and a tracer diffusion coefficient and a mutual diffusion coefficient. Do you remember that concept, Tyler? Is that ringing any bells? Or are you like, oh crap?
Is, but I would like to.
Yeah, let's remind ourselves of that, right? So we said that the tracer diffusion was what happened when you labeled a particle and watched it move around, right? And we said the self-diffusion was when I had a system of all itself, and so I labeled it and I could just watch it move around, as opposed to mutual diffusion when I had gradients of A and B and B and A, right? Okay, so when I get to the dilute limit, right, if I have like if I have a system and I've got all of this, particles in here, and these are all B, okay, and then I have just one A, a single A, right? That's the dilute limit of the diffusion of A in B, okay? And so in that case, I can look at the tracer diffusion of just A and B, right? There's no like gradients or whatever there, okay? So in that case, this diffusion is a coefficient is a constant, and I can pull it out, right? And it's close to the tracer diffusion. So, often there's not just one A, right? We care about something where maybe there's a solute, right? And I've got, a little bit of A, but it's just a dilute, something that's sparingly soluble, okay? And so I've still got a lot of B around, and in that case, the diffusion coefficient is constant, the density is a constant, that can, okay? So in that case, I get rho EWA E is equal to rho DAB grad squared WA plus RA. Okay? So the case of a variable diffusion constant, okay, it's not a constant, we're a function for the diffusion, is way more common in mass transfer than I think it is in heat transfer. I mean, heat transfer can happen. You can have materials that have, variable thermal conductivity, but this is super, super common, and especially in the cases we care about, right? So this simplification here, you have to be careful, about doing that step. Okay, so that's one reason why I wanted to highlight it. Okay, then I just wanted to bring up, okay, there are a lot of other properties that you'll read about that we've talked about in the past. So we had things like ideal gas was something we had talked about, incompressibility. It was something we talked about, and then one more that we haven't talked about, but which is important, an ideal mixture, which if you remember, that's that. So we have Raoult's law, and when you have an ideal mixture, okay? So all of these can have implications for mass transfer, but almost always it only matters if you have multi-component. Okay, so this is when people are talking about multi-component. Okay, this ends up mattering more. There's simplifications that you can make in the interrelationships between these variables. So, or other things like ideal gas lets you use pressures instead of, densities, right? It's easy to use pressures in that case. Incompressibility lets you use things like volume fractions instead of densities if you want, okay? Because in the case of something that's incompressible, rho is equal to a constant, and you can have then you can say rho is equal to 1 over the molar volume of the mixture, okay? And you can mess around with this. Often this is combined with an ideal mixture. And an ideal mixture, you can say that I think what I mean here is this. You can say that the specific volume is equal to the partial molar volume in an ideal mixture. Okay, so there's things like this that are useful in mixtures. You have to start thinking about your thermodynamics of mixtures when you do. Okay, so I don't think we're going to do a lot with multi-component mixtures, but if you care about them, I was reading about them some to sort of help prep for this lecture, and this book is wonderful, okay, on that subject. So this is a book by Ed Kussler called Diffusion. He's a professor at Minnesota. I didn't take this class when I was there, but I knew people did, and this is a great book. And I've been using it. So if you care about multi-component mass transfer, I don't know if you're doing that in your nuclear problem, and you're like, I want to know how to write down 7 species, and I've got all these electric charges and stuff, and I have to worry about that. Go check out Ed Kussler's book. This is the one from the library. So there's another one there, but don't request that one, I guess. Total 2 lectures, or I'll just have to return it late. I'm using it at the moment. Okay. All right. So I think that's where we'll leave it. We'll come back and do dimensional analysis, some examples, and hopefully get a chance to talk a little bit about the equations with multi-component when I go back and revisit momentum and energy next time. Okay? I think that's all I got for you today. So homework due Wednesday. We'll push that back a day. And exam next week. Thanks, everybody.
You don't have to.
I don't know.